Okay, thank you. Well, first of all, I would like to thank Carla and her team for inviting me and for organising this conference. The organisation is absolutely amazing. I should say that I feel a little out of place because I don't do attosecond science and I don't generate high harmonics, but hopefully I have something of interest to you and that could perhaps spark some interest, particularly with theoreticians. So the rationale for our work is to understand biological molecules' response to light. So over the last 4 decades, without a doubt, there's been amazing progress in gas phase spectroscopy, and it's possible to get exquisite amounts of detail into the electronic structure of molecules and molecular dynamics. And also, in terms of theory, electronic structure calculations for gas phase molecules are spectroscopically accurate, and molecular dynamics and quantum dynamics calculations are also possible. But the caveat is that chemistry and biology and almost all technologies take place in the condensed phase, not the gas phase. So what we need to do now, a current big challenge, is to understand the role that a complex environment, particularly my interest in biological environments, plays on the molecular and electronic structure and dynamics. And for that, photoelectron spectroscopy is a really good tool. It's not the only tool, but it's particularly good in my mind because it allows us to compare analogous measurements in the gas phase with those that are made in the solution phase or liquid phase, and then we can unravel exactly what the role of the environment is. So in terms of the structure of my talk, I will start by a little bit of background into liquid jet photoelectron spectroscopy, and then spend some time discussing the challenges in interpretation of the liquid jet photoelectron spectra. And in terms of the science, I will discuss a couple of recent studies from our group on phenol and the GFP chromophore. So phenol is this molecule here, and it's a ubiquitous motif in many biological molecules in life. And it is also one of the building blocks of this green fluorescent protein chromophore, which is this molecule here. And ultimately, we would like to be able to study these biological chromophores in their real native protein environments. But the first step is to understand the difference between the gas phase and aqueous solution. So in terms of gas phase photoelectron spectroscopy, it's relatively straightforward in that we put a photon in, we ionize the molecule, we generate a cation and an electron. If we use UV photons, then very often the UV light is resonant with an excited state of a molecule because most large molecules absorb in the UV to excited pi star states. And with this resonant excitation, we excite vibration energy levels. The molecule can then react and do other things, and we can track this by a time delay between our excitation pulse and our probe pulse. But importantly, there's a general propensity for keeping the vibration energy when you ionize. So the amount of electron kinetic energy we see tells us something about the dynamics in the intermediate state. So this electron kinetic energy distribution contains a wealth of details about the vibrational modes of both the intermediate and the neutral radical after ionization. So when we move to a liquid, there is an immediate complication in that all the molecules are not in the same environment. So this is just a cartoon to illustrate what that same molecule that I've just shown you in the gas phase might look like in a liquid. These are just different solute and solvent configurations. So the arrangement of water molecules around the solute changes the energy levels. So it changes the energy levels of the ground state and also of the ionized state. So we see a spread of kinetic energies. And so this inhomogeneous environment in the solution adds a complication to interpretation of solution phase spectra. A further complication is solvent relaxation. So if we take this last example at the end here and put our photon in, after we've put the photon in, the molecule may relax in response to the ionization process. So this solute and solvent relaxation results in even more of a range of electron kinetic energies that we have to measure. So the interpretation of liquid phase photoelectron spectra is more complicated than in the gas phase. There's obviously technical challenges as well, getting liquids into an instrument where we can measure photoelectrons with the water vapor poses a challenge. It was in the 1970s that Siegbarn introduced volatile liquids into the gas phase and was able to measure photoelectron spectra. But it wasn't until the late 1990s that Froebel first showed that we could use microjets to reduce the amount of evaporation from the surface of the liquid jet, and also use them at high speed so that the liquid can travel through vacuum before it freezes out. And so there have been many X-ray photoelectron spectra of liquids. So this one here is of water, and also of some highly soluble solutes. The trouble is, when you record a photoelectron spectrum of a solute in a liquid, is that the amount of solute is considerably less than the water. So water, if you look at its concentration, it's about 56 molar. And this is an example of a sodium iodide spectrum on the bottom here. That's a 2 molar concentration of sodium iodide, and these are the iodine peaks. Now, the trouble with looking at organic molecules is that most organic and biomolecules have less than millimolar solubilities. So really, their spectra are going to be down here in the noise. And so to subtract them from the water spectrum is very difficult to get these photoelectron spectra. All is not lost, though. We can use multiphoton ionization with UV light pulses. So the key is to keep the sum of the UV light pulses below the ionization potential of the water, so less than 11.3 EVs or so. And also we can exploit the resonances, the natural resonances that the molecule has in the UV. So we can use resonance enhanced multiphoton ionization to enhance the photoelectron signal that we get. And this is a very nice example taken from Steve Bradford's group, where he shows tyrosine, 2 millimolar, in an X-ray photoelectron spectrum on the left, where he didn't see the spectrum, and then using UV photons on the right in a resonance enhanced multiphoton ionization experiment, where he sees a very clean photoelectron spectrum. So there are other challenges too. Having got the molecule in the liquid and understood its energy levels, and then promoted the electron, ionized the electron from the solute, the electron is then promoted into the conduction band of the liquid. And from there, it has to transport through the liquid, and then it has to be emitted from the surface of the liquid. So I'll talk about the transport through the liquid in a moment, but in terms of the emission from the surface, then the scattering at the surface is determined by the electron kinetic energy itself, and the difference between potential energy difference between the bottom of the conduction band and the vacuum level. So this is very much also dependent on the instrument that's being used, and is quite commonly known in photoelectron spectroscopy. So in terms of transport through the liquid, then high kinetic energy electrons will undergo, well, all electrons will undergo elastic and inelastic scattering from the solvent molecules in this transport process. Higher kinetic energy electrons predominantly undergo electronic inelastic scattering, and the inelastic mean-through path determines the probing depth. And there's this famous universal curve that shows how the inelastic mean-free path increases monotonically with photon energy. And so hard X-rays in particular are definitely probing in the bulk. It goes through a minimum around 50 to 100 EV electrons, and then is raised again. So one might then think that the inelastic mean-free path might be longer for low kinetic energies electrons, but this isn't the case. And one might also pay attention to the fact that all these different theories and measurements are quite different in this region. The inelastic mean-free path and the electron attenuation length are really not very reliable for low kinetic energy electrons. For these low kinetic energy electrons, then the elastic scattering cross sections are much larger, so the electrons undergo many more scattering events, and the effective attenuation length determines the probing depth. And inelastic scattering also occurs as a result of vibrational, librational, and bending interactions. with the solute molecules. So Ruth Signorelle has made some nice measurements and compared them with theory to try and determine the probing depth using few EV photoelectrons, which are of interest to UV photoelectron spectroscopy. And the probing depth appears to be of the order of a few nanometers, so we can be confident that we can probe in the bulk and not just surface states. So we need to account for this inelastic scattering in UV photoelectron spectra. And Toshinori Suzuki has made some very nice measurements of the photoelectron spectrum of the solvated electron as a function of a wide range of UV photon energies, and measures different binding energies. And so we need to be able to account for this in our measurements of photoelectron spectra. Ruth Signorelle did some Monte Carlo simulations to try and retrieve the true photoelectron spectrum from these UV measurements and produce this blue curve, which has a peak around 3.7 EVs. And Toshinori Suzuki has made analogous measurements using EUV photons, and where inelastic scattering is almost insignificant, and the peak of these two measurements is in roughly the same place. So armed with all this information, we can now carry out photoelectron spectroscopy. So the two stories I would like to share with you are phenol and the green fluorescent protein. So starting with phenol, phenol is this molecule, and it has pi star excited states in the UV region. And it also has these pi sigma star states, which are dissociative states when along the OH stretching bond. And these are very important in biological molecules, because these dissociative states join these excited pi star states back with the ground state, and have been shown to be very important in relaxation pathways to prevent radiation damage. There's been a huge amount of work in the gas phase, looking at the dynamics on these excited states, both above and below this conical intersection between the dissociative states and the pi star states. Dissociation is very fast if you hit the dissociative pi sigma star state on a femtosecond timescale, and even just below this conical intersection, dissociation can be observed by tunneling through this conical intersection, but it's a lot slower. In the solution phase, the dynamics are very similar in an inert solvent such as hexane. This has been studied using transient absorption spectroscopy. And in water, a more important solvent for biology, solvated electrons have been observed. So following excitation of a higher lying pi star state up at around 6 EV, the second pi star state, solvated electrons were observed on a very fast time scale of around 200 femtoseconds, and also on a slower time scale, having excited below the conical intersection. Phenol has also been studied in terms of its ionization. In the gas phase, the ionization energies are very well known, and X-ray photoelectron spectra have determined that the ionization energies are lowered by about 0.8 EVs when in aqueous solution. So this was our first system that we set out to study and try and understand what was going on in UV photoelectron spectroscopy. So here I'm showing the gas phase UV vis absorption spectrum, which is the black line with the sharp features on it, and the blue curve is the solution phase UV vis spectrum. So here, this is one of our first experiments. We weren't brave enough to go for very low solutions, but its point is 100 millimolar concentrations, so 0.1 of a molar. In terms of what REMPI schemes we looked at, we excited close to the adiabatic excitation energy, then we put more and more energy in the S1 band, and we also excited in the minimum of the absorption spectrum so that we could look at direct detachment from the ground state, and a final experiment up at 200 nanometers in the higher lying excited states. Here's a series of solution phase photoelectron spectra, which are these blue lines, and these are compared with gas phase photoelectron spectra, which are these black lines. So the black lines, particularly when we excite at the adiabatic excitation energy, have got a lot more structure and are very well resolved. And the solution phase photoelectron spectra are all very broad and very structureless. But and on the whole, the solution phase spectra are lowered by about 0.8 EVs in binding energy. So we can fit Gaussians to these solution phase spectra, and we can determine the ionization energies and some other features. So if we look at the 235 nanometer spectrum at the top, this was recorded when we were in the minimum of the UV PES absorption spectrum. So we can see direct detachment processes from S0 to D0 and S0 to D1, two ionization limits. We see peaks at 8 and 8.9 EVs. And then if we account for the inelastic scattering from Toshinori Suzuki's work, then we can see that the binding energies are 7.8 and 8.8 EVs, which are in excellent agreement with the X-ray photoelectron spectra. If we come down in energy when we're exciting the S1 state in a REMPI process, we can see that in all of these we're seeing ionization from S1 to D0 and D1. So this is a resonant ionization process. And if we look on the left, the low binding energy edges, we can see that the fit is not so good on the very lowest binding energy edge. And if we look at these residuals, this corresponds to non-resonant two-photon ionization that competes. And as we're going away from the maximum of the absorption, this competing process plays more of a role in the photoelectron spectrum. If we look at the 275 nanometer spectrum, when we're exciting near the adiabatic excitation energy, we can see that the ratio of the two peaks areas is around 3:1. And we can compare these with some calculated ionization cross-sections, which are also, the ratios are 3:1, so in excellent agreement. If you look more carefully at these peaks, you can see that these orange peaks are moving towards higher binding energy as we increase to the photon energy. And this is obviously due to inelastic scattering that I've already mentioned. So we can plot the electron kinetic energy of these peaks as a function of the photon energy that we put in. And we've done this both for the S0, S1 D0 and S1 D1 ionization processes in aqueous solution. And we can compare this with the S1 D0 in the gas phase as well, because we have that data too. So the gas phase spectra, if we plot the peak positions, the electron kinetic energies of the peak positions as a function of photon energy, we get a gradient of 1, which is exactly what we would expect if we consider that we're putting in extra photon energy into the resonant excitation process and the ionization process. But we get a gradient of less than 1 for the liquid phase analogous measurements. So this is completely due to inelastic scattering. And if we look at the difference between our actual measured lines, which are the solid lines, and where we would calculate these lines to be based on the X-ray photoelectron spectrum measurement, which are these dashed lines, these differences represent the inelastic scattering. And the differences that we see here are identical to those that Suzuki sees in his solvated electron spectra, which gives us confidence that this shifting method is a good way to go. At 200 nanometers, higher in photon energy, when we excited the second pi star state of phenol, we see predominantly a spectrum of water because we're above the ionization limit of water, but we see this residual over here. If we look at this residual more closely, we see a peak around 4 EVs, and if we account for inelastic scattering, this is 3.7 EVs, so we attribute this to the solvated electron, which is analogous to the transient absorption spectroscopy measurements carried out by Steve Bradford and his group. So we've also done some simulations of the spectra. So this grey Gaussian here is our experimental fit of the S0 D0 ionization process to our photoelectron spectra. And we've done some QM EFP calculations to calculate the ionization energy of phenol in an aqueous solution. These are completely non-trivial calculations. And the interesting thing is that the full width half maximum of our simulation is somewhat narrower than the full width half maximum of the experimental fit. And this gives us some idea of the solute and solvent reorganization that takes place during the ionization process. It may also contain some component of EKE-dependent inelastic scattering. So now I think I have a few minutes to quickly discuss some spectra, photoelectron spectroscopy of the green fluorescent protein chromophore. The green fluorescent protein is ubiquitously used in biology and medicine for imaging. The fluorescence is actually from the anionic form. It's the phenol group here is deprotonated at the OH. The fluorescence is very high quantum yield. It has a quantum yield of 0.8. If you unfold the protein, the molecule doesn't fluoresce. So it's this molecule that fluoresces, this anion that fluoresces, but only when it's in the protein environment. So gas phase spectra almost 20 years ago, the absorption spectrum of the isolated chromophore was very similar to the absorption spectrum of the anionic chromophore in the protein, which led people to believe that the electronic structure and dynamics of the chromophore in the gas phase were very similar to that in the protein. However, it doesn't fluoresce in the gas phase. The higher lying excited states of GFP have been proposed to be the states that are involved in light-induced electron donor properties, which are valuable in measuring redox properties in cells. And there have been a wealth of gas phase studies of the higher lying excited states of this group GFP chromophore. So our question was, what happens in an aqueous solution? So the gas phase photoelectron spectrum, it's an anion and it's a fairly large anion, so the detachment energy is very low. It's only about 2.7 EVs, and that has been measured by many groups. Here I've shown the absorption spectrum. So these dots represent the action absorption spectrum of the chromophore in the gas phase, and then the solid black line represents the absorption spectrum of this GFP chromophore in aqueous solution that we have measured. So something I want to point out to you, this molecule really is a perfect illustration of how UV photoelectron spectroscopy can be valuable for these sorts of molecules. It's impossible to get this molecule to dissolve so that we can have high concentrations. The maximum we could get was 13 micromolar. So there's almost no HBDI, and it would be impossible to record an X-ray photoelectron spectrum of this anion. So this is the absorption spectrum. This is the first band, S1, and there's some higher lying states. We've done REMP spectra across this range, and we get photoelectron spectra like this. This is work that we're just about to submit, so there's no reference. We can fit Gaussian to all of these photoelectron spectra at different regions and assign them to various REMP and direct detachment processes. But the important result is that we can deduce that the detachment energy increases by about 4 EVs of the chromophore when it's placed in solution compared to when it's in the gas phase. So I told you that action absorption spectroscopy measurements of the gas phase chromophore have shown that the first excited state in the gas phase is very similar to the first excited state of the chromophore in the protein. It's slightly blue shifted in aqueous solution, but what's interesting is that the detachment energy in aqueous solution is very similar to that in the protein. Also, the pattern of excited energy levels looks very similar to that is in the protein. So our suggestion from all of this is that the aqueous solvent is a very good model for the excited states and for electron detachment in the protein. So perhaps the redox properties of the green fluorescent protein chromophore in aqueous solution are similar to those in the protein. So in summary, I hope I've shown you that photoelectron spectroscopy, comparing photoelectron spectroscopy of isolated molecules in the gas phase and in complex environments in the solution, promises to provide a useful approach to unraveling the role of an environment on electronic structure and relaxation dynamics, and that this could be used for benchmarking theory because we're making analogous measurements always of the binding energies. In Phenol, we were able to illustrate the impact of inelastic scattering, and by comparison with theory, show that we can potentially extract information about solute-solvent relaxation processes. In the green fluorescent protein chromophore, it's an anion, so the aqueous environment raises the vertical detachment energy by more than a factor of 2, by 4 EVs. And the aqueous environment appears to be an appropriate model for ionization and dynamical properties of the higher lying excited states in the protein. But there are still many challenges for liquid microjet photoelectron spectroscopy. There's a lot of information in the spectra and we can't get it out yet. The wavelength dependence of inelastic electron scattering and the probing depth of 6 EV electrons is really unknown. And if we could understand this and model this, then this would allow us to get a huge amount of extra information from our experimental photoelectron spectra. It would allow us to extract details of solute-solvent reorganization energies much more readily. In terms of quantum chemistry calculations, accurate calculations of excited states and ionization energies in aqueous solution are really difficult. And we really need to advance the computational methods that we can use to calculate these things fairly accurately. And if we have all of this information, if we can understand, if we can calculate the processes in the using quantum chemistry accurately, and we can measure or calculate how the electrons, when they're released from the molecules and anions, scatter through the liquid and then emerge from the liquid, then we'll be in a position to simulate photoelectron spectra, which I think will be a very exciting thing to do. So I'd like to finish by acknowledgements. This is my group as it used to be when I saw them in real life. This is my group as I see them now when we had a celebration. We're not always drinking wine. And so I'd like to acknowledge all the people in the first line here who've contributed to the work I've shown. And in the next 2 lines, some theory and synthetic chemistry collaborators. And I'd like to thank you for listening.
Thank you very much for, I don't know if you can hear the applause. Anyways, thank you very much for a wonderful talk with impressive results. I would encourage anybody who is interested to either raise your hand or place your questions in the Q&A box. Maybe I can start. I have one. So on the phenol work that you have shown first, you talked about basically the, what was it, the pi sigma star that basically takes the energy back down to the ground state and basically relates to the dissociation along the OH, if I understood it right. Yep. And I was wondering, you talked about the difficulties, of course, or the challenges taking inelastic scattering into account to interpret the measurement. How about, is there a chance to really describe the vibronic couplings in the molecule, which is probably very important for these kind of conical intersections and this energy transfer?
Well, there has been an awful lot of work on this in the gas phase.
Mm-hmm. So, in the liquid, I mean, right? Which is what you like to do, right?
Yes. Yes. When we will soon be measuring these processes in a time-resolved way, and so these are our next experiments that we'll be doing when we can get back in the lab properly, and we will see the effects of different timescales, I imagine, but the subtleties in terms of the line shapes, we will be able to observe changes in line profiles in spectra, but on top of what the molecule and the solvent are doing is the fact that we've got the inelastic scattering. So if we can extract the inelastic scattering part, which we are also trying to do, then we will be left behind with how the shapes of these broad features might change. So I think we will be able to get some extra information about the role of the solvent on the couplings between these states from our spectra. But there's a lot of work to do. I mean, we need to do the theory of the electron emission process as well as the theory of the the chromophore in the solvent, both of which are slightly non-trivial, I think.
I guess it's a large theoretical challenge. I saw you, of course, you use state-of-the-art coupled cluster, then also this EOM method. But then to add probably the time resolution to it will be quite challenging, right? But interesting.
Oh, for sure. So actually, to do those calculations on an evolving potential surface away from the Frank-Condon region will be challenging, yeah.